Hello, and welcome to another Ursa example video. In this one, we're going to solve these three integrals. The first one is int dx of x squared, the next one is int dx of e to the x, and then int dx of x times e to the minus x squared. So for the first one, int dx of x squared, we just need to use the power rule, and Ursa has the power rule. So typing in I.power rule, we can find that rule, and you give it the name of an arbitrary constant that you want to use in the outcome of the integral. So running that rule, we get x cubed over 3 plus c, which is my arbitrary constant. Now, the next integral is also very simple. The integral of e to the x dx is just e to the x again, plus an arbitrary constant. And here I can put in a different letter if I want, or if I happen to know that my arbitrary constant is going to be 0, I can just put in 0, and then simplify this. It is an arbitrary constant, so you can put in anything. And now for this final integral, it's int dx of x times e to the minus x squared. For this one, we're going to need to use substitution. And substitution is an integral tactic where you identify the integrand as a function of something times the derivative of that thing. And then you can do this certain rewrite on the integral. And in this case, we have the integral dx of x times minus x squared. So this is a function of minus x squared times x, which is very close to the derivative of minus x squared. So we will be able to use substitution. The only thing is, in order to use substitution, you need to have the integral in the form a function of something times the derivative of that thing. But we have x here. We don't actually have the derivative of minus x squared. And that's what we need. So how do we change x into the derivative of minus x squared? I'll let you think about that for a little bit, and leave your answer in the comments. Okay, the way that we change x to the derivative of x squared is by using the fundamental theorem of calculus. This replaces a formula with the derivative of its integral, since these are inverse operations. So now we have d dx of int dx of x. And we just need to solve the integral. So the solution to this integral is found using the power rule again. And since we're trying to find d dx of x squared here, we know that the arbitrary constant's going to be 0. There's nothing else it could be. So we can just simplify that away, plug in 0 and simplify it. And now we need to do a couple more things. We need to factor out the 2. Or the 1/2. And since the derivative here, this thing that we're taking the derivative of needs to exactly match the subformula that we want to substitute. And so we really need a minus sign in here too. And we can add that with a rule called double neg intro, which introduces a double negation. And this is valid because minus minus something always equals that thing. So now we've got minus minus x squared, and we can pull out one of those minus signs out to the top of the formula using the commute rule. Commute neg pulls minus signs out, and we need to run that bottom up to pull the minus sign all the way out from that derivative up to the top of the formula. So now we've got the integral in the form. It's the integral of d dx of minus x squared times e to the minus x squared. And now we can use substitution. So I'm going to invoke the substitution rule, and I'm going to use a variable called u. So when I invoke this rule, we get this. And this is... this is the integral with minus x squared substituted out for u by the substitution rule. And really what we have here is, often in math, when you're using substitution, you will introduce your variable, you'll solve the integral, and then you plug the original value back in for that variable. So here we substituted with u equals minus x squared, and what it gave us is this lambda expression applied to minus x squared. And the lambda expression is u goes to integral du of x u. So all we need to do is solve this integral and then plug in minus x squared back for u. So to solve this integral, we can say I.exp again. And I'm going to use the constant c. And now we just need to plug in minus x squared back into this lambda expression, which is done with the lambda.reduce rule. So now we've got minus 1/2 e to the minus x squared plus c, and we can simplify this and distribute in the minus sign. And now, really, this is an arbitrary constant. C is an arbitrary constant, so minus 1/2 of c is also an arbitrary constant. And we can clean this up a little bit in a couple different ways. One way is that we can just use the builder.set rule to replace it with c. But if we had multiple c's in the formula and we wanted to be a little bit more careful, another way that we could do it is we could use builder.apply to take c and replace it with minus 2 times c. So that will kind of invert this minus 1/2. And then we can run this bottom up on the entire expression tree, replacing every occurrence of c. So after running that, c has been replaced with minus 2 times c, and then we can simplify, and then we just get plus c. So that's another way to do it if you want to be careful and just replace c with something everywhere. So that's it. That's the solution to this integral. Minus 1/2 e to the minus x squared plus an arbitrary constant. See you next time.